Hello everyone. So welcome you all for the post-contest discussion of Codeforces Pinely Round 4. Let's start with the discussion. So this is the first problem. The name of the problem is maximize the last element.
So you are given an array A of n integers where n is odd. In one operation, you will remove two adjacent elements of the array. And in the second operation, you will remove two adjacent elements of. For example, if you are given an array something like this, and if you decide to remove these two adjacent elements, then you will be left out with this array. And in this array, if you decide to, let's suppose, if you decide to remove these two adjacent elements, in that case, you will be left out with these three elements. They will be concatenated and you will be left out with array 479. However, if you have the desire to form the array something like 7 to 9, then you can't do this because in that case, you will need to remove this 4 and this 4, and since these elements are not adjacent, you can't remove them. Now you are allowed to do this operation repeatedly until you have exactly one element in the array left. So the question is that what is the maximum possible value of the remaining element in array A? So I hope the question is clear. Let's see how we can do this. So the question is something like this. Wait a minute. Yeah. So the question is something like this, that you have some array, let's suppose 4, 4, 7, 2, 9, and you can choose any two adjacent elements and remove it. And you can do this operation repeatedly. For example, if I decide to remove these two adjacent elements, I will be left out with 4 to 9. And then I decide to leave these two adjacent elements, I will be left out with only 9. And the remaining element will be 9. Similarly, if I want this to be the remaining element, what would I do? I want 7 to be left at the end. So what will be my aim? My aim will be that all the elements towards the left of 7 is removed and all the elements towards the right of 7 is removed, isn't it? So is it possible for me? Yeah, it is possible. Why? Because the number of elements towards the left of 7 are even and number of elements towards the right of 7 are also even. Now, what does this mean? This means that just imagine, since we are removing elements two at a time, so if there are even number of elements towards the left of 7, can I remove all those elements? The answer is yes. If there are even number of elements towards the right of 7, can I remove all of them? The answer is again yes. So if this is so, then I can get 7 at the end. But just imagine if the numbers were something like this: 7, 4, 4, 7, 3, 2, 1, 6. If the numbers were something like this, and now I want you to remove two, and now I want you to get 7 at the end. Would you be able to do that? Because if you want 7 at end, what you want? You want that all the elements towards the left are removed and all the elements towards the right are also removed. But is it possible for me to remove all the elements that are in the left hand side? It is not possible, right? Because at a time we are removing two elements. And since over here we have three elements, so if we remove any two elements, we will be left out with one element. And since you have been given that the value of n is odd, so if we are not able to remove any elements towards the left hand side, we would not be able to remove all the elements in the right hand side too. Because if the left hand side contain odd number of elements, so right hand side should also contain odd number of elements, because if that is the case, then odd plus odd will become even plus this element 1. So the total number of elements will come out to be odd. So if there are odd number of elements towards the left of any element, I can be sure that this particular element can't be left out at the end. And if there is a number and there are even number of elements towards the left of this particular number, so I am sure that I will be left out with this particular number. I can be left out with this particular number because if there are even numbers towards the left, there will be even numbers towards the right as well. because in total you have given in the question that in total you have odd number of elements. So if you have even elements at the left, you have to have even elements towards the right, because in that case only the total number of elements will come out to be odd, even plus 1. So the question now becomes clear that for all the indexes I, for which the number of elements towards the left is odd, you can't be left out with that number. So for all the indexes I for which the number of elements towards the left are even, just take max of all those and that will be your answer. Because the question was that you need to find the maximum of all the possible remaining elements, isn't it? All the possible elements that can be retained till the end. So we know that for all the indexes whose the number of for whose the number of elements towards the left are even, those can be kept till the end. So just take max of all those and you will be done. So how for all, if you look to the for if you consider the zero based indexing format, so you will look that for all the indexes that has the value even, there are even number of elements towards the left, isn't it? So you simply need to take max of all the values present at even indexed position. That was the logic. So let's see the code. So yeah, just take the input n, initialize your maximum to 0, take the input of all the numbers. If the value of n is 1, simply print v of 0 and return. You can even skip this case, it's not needed. Otherwise, just run a for loop for all the indexes, and if the index value is even, just consider that element in your while taking the maximum. So if I modulo 2 is equals to 0, just turn maxi equals to max of maxi, comma, p of I. And at the end, just print the maximum value. So that's the code for this question. So let's jump on to the second question for the day. So the name of the question is and reconstruction. Let's go through the problem statement. You are given an array B of n minus 1 integers. An array A of n integers is good if Bi is equals to Ai and Ai plus 1 for all I from 1 to n minus 1, where this symbol denotes the bitwise AND operator. So you need to construct a good array or report that no good arrays exist. And you are also given that Bi lies in the range of 0 to 2 power 30. And you have 10 power 5 numbers at max. The value of n is in the range of 10 power 5. So for each test case, you need to output a single integer minus 1 if no good arrays exist. Else, if it exists, you need to output that particular array. That is the n integers, the elements of the good array A. So let's understand what the question wants us to say. So according to the question, you have n numbers. You have given n minus 1 numbers. And this forms an array B, that is B1, B2, B3, B4, B5 up till Bn minus 1. Now you need to construct an array A such that if you have the array something like this, A1, A2, A3, A4, A5, A6 up till An, then you would be able to write A1 and A2 should be equals to B1, A2 and A3 should be equals to B2, A3 and A4 should be equals to B3, and so on till An and An minus 1 should be equals to Bn minus 1. This should be possible. So this is the question for you. So how we can do this? So to solve this fact, when we are doing AND operations, so for a bit to be 1 in the AND operation, the corresponding bits of both the numbers between which we are doing the AND operation should be 1. If these two bits are 1, then only we will get 1 as a result. And if any of the bits is 0, like in this case, or this case, in both of these three cases, you will get the end result of the AND operation as 0. This thing should be clear. If this thing is clear, now the question becomes very easy if you attempt the question in the way they have given you. Like they have given you these things now. Like do A1 and A2 B1, A2 and A3 B2, A3 and A4 B3. This is something given. Just do the same way. What do I mean by that? See, you are given B1, okay? And what you want? A1 and A2 should be equals to B1. So can I say that all bits that are set in B1 should be set in A1 as well as should be set in A2? Can I say this? Can I say this? That all the bits that are set in B1 should be set in A1 and as well as should be set in A2. So just make A1 equals to B1. By doing that, what basically happens is that all the bits that are set in B1 become set in A1 and also do A2 equals to B1. Do this thing as well. Now come to B2. Now come to B2. When you come to B2, now all the bits that are set in B2 should be set in A2 as well and should be set in A3 as well. So let me write this. All bits set in B2 should be set. By set, I mean that the bit is turned on. That is the value of the bit is 1. So all bits that are set in B2 should be set in A2 as well as A3. But can I say this that there should not be any bit position that are unset in B2 but set in both A2 and A3. Can I say this? Because if there is any bit, we have in total 30 bits, right? Because you are given that the numbers are in the range of 0 to 2 power, lesser than 2 power 30. So in total, we have 30 bits. So if any of the bit is such that it is set in A2, it is set in A3, but it is unset in B2. If that is the case, will I be able to produce A2 and A3 equals to B2? Because since if this bit is set in A2 and it is also set in A3, so when I do the AND operation, the resultant bit will also be set in B2 as well. But I am given that this particular bit is not set in B2. It is the case, like this is the case. So I can say that there should not be any bit position that are unset in B2 but are set in both A2 and A3. So how now I am going to apply this to my question? So for applying this to my question, what I will do is, while I am doing this, that okay, for every bit in B2 that is set, that particular bit should be set in A2 and that particular bit should be set in A3 as well. So can I maintain something for A2 that what all bits are not allowed to be set? So if I am able to maintain something like what all bits are not allowed for A2 to be set, so while I am setting them for B2, and if there is a bit something like that, so I will return -1. What do I mean by that? Let me tell you. Let's suppose as 1011. Okay. You have B2 as, uh, let me write it like this. Let's suppose you have B1 as 1010. You have B2 as 1101. Okay. And you have B3 as 0101. I will change it. Let me construct the example. So what you will do is, first of all, you will make A1 as 1010 and you will make A2 as 1 0 1 0 as well. Now if we AND these two, we will definitely get B1. Now for B2 to be set, for B2 to be set, for A2 and A3 to produce B2, all the bits that are set in B2 should be set in A2 as well as in A3. Can I say this? Now, when I say this, I know that for A2, these two bits are set, and the requirement is that these two bits should be set, isn't it? These two bits should be set. So what I do for A2, I make this bit as also 1 and this bit as also 1. This is something I make. Okay. And for A3, I make something like this. For A3, I have made something like this. Now coming to B3. Now coming to B3, if you see, if I just make B3 like this, if I simply turn this bit for B3 as well. So, okay, if I have B3 something like this, now for A3 and A4, all the bits that are set in B3 should be set in A3 as well as in A4. Now, if I try to set all the bits that are to turn all the bits on for A3 that are turned on in B3, so what I would do, I would make this bit as 1. But if I make this bit as 1, so now if I AND A2 and A3, I should have this bit as turned on in B2, but I don't have that. And hence, I can say that with this particular configuration, I can never construct I can never construct a good array, isn't it? So how I was able to identify that I can't turn this bit on? How I was able to identify? By doing something like this. I can do something like this, that just make this bit as 0. It was 0 initially. And once I have A2 as 1 1 1 1 and I have A3 as 1 1 0 1, so now I know that A2 and A3 is giving me B2. It's all right. So can I say that if there is any bit that is turned on in A2 and it is still not turned on in A3, so I can never turn this bit on, because in future if I try to turn this bit on, because when I will turn this bit on, when I will try to satisfy the condition for B3, but it should not be turned on, because if it is turned on, then A2 and A3 will produce 1 at this bit position, but it should be 0. So what I can do is I can simply mark it as -1. Instead of 0, I can simply mark it. I can maintain one vector of size 30 and I can simply mark it as -1, saying that, okay, you can't be turned on in the future. And in future, since it is turned -1, and in future, since when I was trying to turn this particular bit on, I will try to turn this particular bit on in A3. But this particular bit will tell me, no, I have the value -1 in me. You can't turn me on. And if I get something like this, I will simply print -1. And if till the end you don't get something like this, so you can simply, you know that which all bits needs to be turned on. So you can simply construct your answer by that. So you will simply have the vector. You will have some bit positions that are turned on. So you will simply initialize your answer to 0. Just move on to each and every index I and just or your answer with one left shift. I. If you do something like this, so you will get will be done. So what was the logic? We did the same thing as mentioned in the question. We just tried to construct a good array by looking at the numbers, and we knew that there are some bits that can't be turned on in the future, even if some numbers require them to. So we simply marked them with -1, and in future, if we try to turn them on, we are simply telling that no, I can't be turned on because of my previous numbers, and hence I need to return -1. I can't construct a good array. So that is the logic for this question. Let me go through the code once. Okay. So we first of all took input of the array B, that is of size n-1. Then we constructed a vector n, a vector of vector int n, and every number will have a size of 30 because there are at max 30 bits. So for every number there are at max 30 bits. Now we went on for the first number we are populating by ourselves. So for the first number what we are doing, we are going to each and every bits individually, and if that particular bit is set in the first number of the B, so that particular bit needs to be set in the uh, 0th number also and the first number also. So for the 0th number in its ith bit, we are setting the value as 1. And for the first number also in the ith bit, we are setting the value as 1. Now we individually went to each and every remaining numbers. That is iterated our j loop from 1 till n minus 2, that is j less than n minus 1. And for every jth number we know, and for every jth number and for every ith bit, so we went to each and every bits correspondingly. So like for every number b2 we will go to each and every bit of b2, isn't it? So if that particular bit is set in b, that is b of j, and one left shift I produce me some result, that is that particular bit is set in j. So first of all, I will check that if I can turn that particular bit on or not in my number Vj. So for any number Bj, I have two numbers to populate, Vj and Vj plus 1. So I will first of all check if I want to turn some bit on in Vj, so that particular bit can be turned on or not. So if that particular bit does not have the value -1, I can simply turn them on, right? So if v of j of I is equals to -1, this means that I can't turn the ith bit for this jth number in the array v, and hence I will print -1 and simply return. And if this is not the case, I will simply turn this bit on in jth number as well as in j plus 1th number. Once I do this, once I am completed with this, what I will do is I will just see for each and every bit that what all bit positions are there that are turned in v of j but are off in v of j plus 1. If there are any bit positions something like that, then for v of j plus 1 I will mark them as -1 because in future I can't turn them on, isn't it? So what I did, I iterated over all the bits, and if there is some ith bit for which in the jth number the value is 1, but in j plus 1th number the value is not 1, in that case I will simply mark it as -1. Once I am done with this, and if I have not returned till now, this means that yeah, I was able to construct some good array. In that case, I went to each and every number, initialized my answer to 0, went to each and every bit and just looked for which all bits are set and simply added that to my answer. So went to each and every bit from j equals to 29, j greater than equals to 0, j minus minus. If for the ith number the jth bit is set, so simply ORed my answer with one left shift j. Once I am done with this, I simply print my answer. So that is the logic for this question. We have not implemented anything that is like requires any mathematical reasoning or not. There can be many methods to solve this question. There is a method with some mathematical reasonings as well that will directly help you to lead to the conclusion. But what we tried is that if we are not able to approach the question that way, so by just doing the way it's mentioned in the question, we are able to reach to a solution, isn't it? So yeah, this is the solution for the second code. So let's jump to the third problem. So the name of the third question is absolute zero. So let's go through the problem statement. You are given an array A of n integers. In one operation, you will perform the following two-step move. You will choose an integer x. The x lies between 0 and 10 power 9, and replace every value of the array A, that is every AI, with absolute value of AI minus x, where this denotes the absolute value. So for example, if this is the array and you chose x as 8, so the array will be changed to modulo of 5 minus 8, comma, modulo of 7 minus 8, comma, absolute value of 10 minus 8, that will be 3, 1, 2. So you need to construct a sequence of operation to make all elements of A equal to 0 in at most 40 operations, or you need to determine that this is not possible and you do not need to minimize the number of operations. Okay. So you are given the number of test cases, the size of the array is at most 2 into 10 power 5, and the elements lie in the range of 0 to 10 power 9. Okay. And it is guaranteed that the sum of n over all test cases does not exceed 2 into 10 power 5. Okay, well, okay. So this is the question that you can choose any x in one operation. Just subtract every value of the array with that x and take the absolute value, and you will be left out with some array after one operation. So you can do at most 40 such operations, and you need to determine if you can turn all these numbers as zero or not. And if so, if that is the case, you need to output the number of operations that you are taking and the k integers as well. Okay. So how to approach this question? So you are given n numbers. Okay. What is the range of this number? The numbers are lying between 0 and 10 power 9, isn't it? So can I say that every number ai is within 0 to 2 power 30? Can I say this? Okay, great. Now I want what I want. That okay, if this is A1, this is A2, A3, A4, A5, A6, A7. If I choose some X, what I will do, I will simply do A1 minus X mod. I will replace A1 with A1 minus X absolute value, A2 minus X absolute value, A3 minus X absolute value, and so on for every number. And I am doing this for each and every number. So if I have an array, if I have an array that contains both even numbers and odd numbers. If I have something like this, okay, if I have an array that contains both even numbers and odd numbers, will I be able to make anytime the all the elements zero? Let's suppose I have only two numbers, I have only 2 and 1. So can I, in any time in future, make both these elements of zero simultaneously by doing any number of operations? Will I be able to do that? Okay, if I am, let's suppose I selected the value of x as 2. If I do so, this value will become 0, 2 minus 2 mod will become 0, and 1 minus 2 mod will become 1. Okay, I have 0 and 1 now after doing one operation. Now, what should I choose? I have the option that I can either choose 1 or the value is greater than 1 or something like that, but I don't see any x via which I can make both these values 0 simultaneously, isn't it? So this led to me the conclusion that if my array contains both even and odd numbers, then my answer will always be -1. Okay, this thing is very much clear. But what if all the numbers are even or all the numbers are odd? What in that case? What should I do? Okay, just try. Okay, if I have the numbers in the range 0 to 10, and if I choose some x, if I choose some x in between 0 to let's suppose 5. Okay, if I choose some x in between 0 to 5, let me tell you, it is 0 to 5. Yeah, let me include both these. Wait a minute. If I choose some x, um, if I choose some x in between 0 to 5, okay, if I let's suppose choose 5 as my x, if I choose 5 as my x, can I say that if there are any number in the range 0 to 10, let me take that particular example only. If I have the array, let's suppose 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and if I am choosing the value of x as 5 and I perform the operation, just write down what will the numbers be after operating it with x equals to 5. Once I operate with it with x equals to 5, what will be the remaining numbers? The numbers will be 5 minus 0 mod 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5. So can I say that when I apply the operations with the maximum number was 10, So when I apply the operations with 10 by 2, that is x equals to 5, the numbers come in the range 0 to x. Can I say this? Can I say this? So this leads me to the logic that, okay, if I have initially numbers in the range to 0 to 2 power 30, and if I simply operate it with 2 power 29, if I keep the value of x as 2 power 29, so after applying the operations, my numbers will come in the range to 0 to 2 power 29. Similarly, after this, if I apply the operation with x equals to 2 power 28, my the remaining numbers in the array will come to 0 to 2 power 28. Similarly, after this, if I apply the operation with x equals to 2 power 27, my numbers in the array will come down in the range to 0 to 2 power 27. And if I continue this till x equals to 2 power 0, if I continue with till x equals to 2 power 0, my numbers will come in the range from 0 to 2 power 0. Isn't it? My numbers will come down to the range of 0 to 2 power 0. That is, my numbers will come down in the range of 0 to 1. Now I know that if all the numbers are either even or odd, that is something that I have already concluded. Now, if all the numbers are odd, if all the numbers are odd, then you will observe one thing, that since the last operation that we are doing is with x equals to 2 power 0, like before, let me just go through the last two operations. The last two operations are when we have the numbers in the range 0 to 2 power 2, and then we choose the value of x as 2 power 1. That is, we chose the value of x as 2. Okay. Now, after doing this, the numbers will come down in the range of 0 to 2 power 1. That is 0 to 2. So this will be the range of numbers, isn't it? Okay. So now, one thing that is very much clear, that if all the numbers are odd, then in that case, if we choose the value of x as 2 power 0, that is the value of x as 1, so my numbers that will be left out will all be 0. Because the numbers were initially odd, we every time subtracted them with some even number. We were every time subtracting with it with either 2 power 29, 2 power 28, 2 power 27, something like this. Till 2 power 2, we were every time subtracting it with even numbers, isn't it? So now we know that odd minus even will every time result to odd. So if we came out with the numbers in the range from 0 to 2, so I am pretty sure that this particular number will come down to 1 only, because the only odd number in the range 0 to 2 is 1. So now if I choose a value of x as 1 and subtract every number with 1, I will I will get the resulting number as 0. But if all the numbers were even, in that case, now if I choose 2 power 0, that is x equals to 2 power 0, that is 1, all the numbers will come down to 1. So can I say that if all the numbers are even, in that case, I will require one additional operation, and for that operation, my value of x will be 1. And in case of if all the numbers are odd, I would not require any additional operation. And after doing only these operations, that is choosing a 2 power 29, then 28, then 27 up till 2 power 0, my resultant array will contain all zeros. So this was the logic behind this question, that okay, if all numbers are not odd or all numbers are not even, we were not able to produce any result. But if this was not so, that is either everyone was odd or everyone was even, so we decided that okay, since we are taking the modulo values, so take the modulo value, and so just try to decrease the range of numbers that we can have. So initially, since the range of numbers was from 0 to 2 power 30, we decided to choose 2 power 29, then 2 power 28, then 2 power 27, and this how we were able to reduce the range of numbers. And then we sorted out the case for if all the numbers are odd or if all the numbers are even, then what could be the possible result. And on basis of that, we decided that if all numbers are even, then we need to do one extra operation, that is x equals to 1. So this was the logic behind this question. Let's see the code. Okay, so first of all, we are checking that if all numbers are odd or all numbers are even or not. So for all numbers, I simply marked f1 as initially false, and for even numbers, I marked f2 as false. Now I iterated over the vector. If the value is odd, how to check if the value is odd or not? By just doing AND with 1. So if the value is odd, in that case, mark f1 as true. Else, if it is not odd, then it will definitely be even. Then in that case, I'm marking f2 as true. Now, if after coming out of this for loop, both f1 and f2 are true, this means that we have both the odd numbers and the even numbers in the array. And we have already discussed that if that is the case, we need to print -1. So simply printing -1 and returning. And if this is not the case, I am constructing my answer. So simply going from every number till 29 till from 29 to 0. And just in my answer, I am pushing back one left shift I. That is 2 power 29, 2 power 28, 2 power 27 up till 2 power 0. And if all the numbers were even, that is if f2 was true, in that case, I am doing one additional operation. And in that operation, I am choosing the value of x as 1. So in that case, I am pushing back 1 in my answer. So at the end, what we need to do, we need to print the number of operations and the value of the x as well for each and every operation. So simply printing the size of the answer, that is the number of operations. And then in the new line, printing all the values of x simultaneously. And once I am in, I am just printing a new line and the code is done. So this was the code for the third problem. I hope all of you got it. So let's jump on to the fourth problem for the day. So the name of the problem is prime XOR coloring. So let's go through the problem statement. You are given an undirected graph with n vertices numbered from 1 to n. There is an edge between vertices u and v if and only if u XOR v is a prime number where XOR denotes the bitwise XOR operator. Okay. So color all the vertices of the graph using the minimum number of colors such that no two vertices directly connected by an edge having the same color. Okay. So how we can do this? So what is the question? Let's understand the question first. So in the question, you have n vertices and like every vertex have the value. Like if there is the ith vertex, so this vertex have the value I. Now there is an edge between two vertex. There is an edge between two vertex. If and only if when we do the bitwise XOR between these two vertex, the resultant value is a prime number. Like for the bitwise representation of 1 is something like this, and the bitwise representation of 3 is something like this. And now if we perform the XOR operation between these two, the resultant answer will be this, which is 2. And we know that since 2 is a prime number, so there will be an edge between node 1 and node 3. Now the question says is that if there is an edge between two vertex, in that case, every time I need to color them with different color. Like if I am coloring one with, let's suppose in this case, I colored one with purple. In that case, I need to color three with some different color. That is, let's suppose green. So the question says that if you are given n vertices, then just tell me what are the minimum colors that you need. What are the minimum colors you need to color all the vertices? So that is the question in front of you all. So how to solve this now? So looking at the question, it becomes a bit complicated to think that, okay, how we can do this, because we have 10 power 5 numbers. Okay. We are told that we have an edge between two numbers only if the bitwise XOR between them is prime. So our mind may just drive us to something that, okay, if we are talking of prime numbers, so let's find out all the prime numbers. Let's find out all the prime numbers, and for every prime number, just see that which two numbers, XORing which two numbers lead us to that prime number, and just color them differently. But this method becomes a bit complicated because you are talking of two numbers, then you are talking of two numbers, then how will you separate them? That how to keep them? Somehow it becomes complicated, and it also will produce TLE because how many numbers produce this prime number on XOR also becomes a tedious task, isn't it? So okay, this process will not work. So what is the other thing that we can think? Other way we can think. So looking at the test cases is something that would be very helpful for this question. Like in the test cases, they have given the test cases like that if you have a look to the test cases once, many things will come to your mind. In the test cases, they have given number of test cases are 6, and they have given you the answer for 1, 2, 3, 4, 5, 6. And if you look the answer for 6, the answer for 6 is 4, isn't it? That is, you minimum require 4 colors for the node 6. So this led you to the conclusion that for all the numbers that are greater than equals to 6, you will require at least 4 colors. At least 4 colors are required. You can't, because it's given only that for n equals to 6, you will require 4 colors. So if I am talking of any number greater than 6, I will definitely require 4 colors because those 6 numbers are also coming in that. The initial 6 numbers, isn't it? Okay. Then this leads me to think that, okay, if I have the value of n as 7, do I require one more color? Do I require one more color? This is the question that comes in front of you all, and you need to solve this. So, you know that since you require at least 4 numbers, so you can think in such way that, okay, every number that I have can be represented in, if I represent it in modulo 4 form, so every number can be represented in the form of 4k plus I, where I lies in the range from 0 to 3, isn't it? Because every number on division by 4 will either give remainder as 0, remainder as 1, remainder as 2, or remainder as 3. So every number can be represented in this form. If I write the binary representation of this, so what basically it means? It means that the last two bits of the number have total 4 possibilities. Either the bits are 0, or the bits are 1, or the bits are 2. Sorry, what I'm writing. Wait, give me a minute. If I talk of last 2 bits for the number, so what can be they? Whatever is the number, I don't just care. Just try to think for the last 2 bits. Because on division by 4, every number will either give 1, 2, 3, or 0, isn't it? So last 2 bits will either 4, that is 2 power 2. We will get last 2 bits of the number. So last 2 bits can either be 0, or it can be 1, or it can be 2, or it can be 3. These are the only 4 possible types of numbers, isn't it? Every number n can be represented in this form. Whatever over here, we don't actually care, but every number can be represented in this form, isn't it? Now just try to think. If I am taking two numbers of this form, if I am taking two numbers of this form and doing a XOR operation, what would be the result? There would be something over here, but in the last 2 bits, we will get 0. This will be the result. Similarly, if I am taking numbers of this form and doing the XOR operation, so what will be the result? There will be some set of bits over here, but the last 2 bits will be 0. Similarly, if I take the numbers of this form and do simply a XOR operation between them, what will be a number? What will be the resultant number? The resultant number will have some combination of bits right over here, and we will have last 2 bits as 0. And similarly, if we do the same thing for this, that we have some numbers of form this and doing the XOR with some numbers of form this again, then if we do the XOR operation, we will get some set of bits over here and the last 2 bits as 0. So the common thing in all of these is that the last 2 bits are 0. And can I say that if the last 2 bits are 0, So the number is divisible by 4. And if the number is divisible by 4, will that number be ever be prime number? The answer is no. So can I say that for any numbers greater than equals to 6, I will require only 4 colors? Give me a minute. Oh, yeah. So I will require only 4 colors. And by using that 4 colors, I will be able to make the solution, because I know that at least 4 colors are required. That is only already given in the question with the example of n equals to 6. Even if this test case was not given, you need to come out till n equals to 6 for figuring out what's the minimum colors required, and then you can do the same way that we have already discussed. So you require only 4 colors. And how are you going to allot the colors? So every number that on divisible by 4 gives the same remainder, just give them the same color. Like for example, 1, 5, 9, these all will be given the same color. Let's suppose 1. These all will be given the same color. So what we are going to do, if we have the numbers, let's suppose we have 7 numbers, 1, 2, 3, 4, 5, 6, 7. We will print that the number of colors we require are 4. And what are the colors that we are going to allocate? So we know that 4 modulo 4 will come out to be 0. And since we need to allocate colors, if we just look, give me a minute. Yeah. So colors lies in the range of 1 to k. That is, you need to start coloring from 1. So since 4 modulo 4 will come out as 0, so you need to color it with some number greater than 0. So what I would do is I will simply color every number I with I modulo 4 plus 1. So basically I will color 1 with 2, 2 with 3, 3 with 4, 4 with 1. Then again 5 with 2, 6 with 3, 7 with 4, 8 with 1, something like this. Or you can do the any way you want. You can color it something like this: 1, 2, 3, 4, then 1, 2, 3, 4, then 1, 2, 3, 4, and continue till you color all the n numbers. Just these 4 numbers should form a set, because what we have decided that every number that on divided by 4 gives the same remainder will be colored same. Once you figure out that, then you can color it in any order you want. Okay, the order does not matter. So this was the logic behind this question. So if we jump to the code, so what I have done is till n equals to 5, I have handled it explicitly, writing exactly, actually copying what actually was mentioned in the test cases. And then if the value of n is not equal to 5, that is the value of n is greater than 5, in that case, I am just printing 4, that is the number of colors I require, that is, and just simply printing I modulo 4 plus 1. If I do so, then I will get the correct solution. So this was the logic behind this question, that looking at the test cases made the question easy. And if someone like missed the test cases or just forgot to see the what actually was mentioned in the test cases, then would find some some problems while solving this question. Like you need to first of all figure out that till n equals to 5, okay, I require only 3 colors. And then from n equals to 4, and from n equals to 6, for n equals to 6, we require at least 4 colors. And once you figure out that, then you can just easily figure out that, okay, if for n equals to 6, we require 4 colors, then we will not require much more, any other color from n equals to 7. Because if 4 colors are required, then we know that this is only the possible combinations that I have. Like these are the possible combinations I can have. I can color them same, isn't it? So yeah, this was the logic behind this question. So let's jump on to the fifth question for today. The name of the question is coloring game. So let's see what the problem statement has for us. So this is an interactive problem. Consider an undirected connected graph consisting of n vertices and m edges. Each vertex can be colored with one of the 3 colors, that is either 1, 2, or 3, and initially all vertices are uncolored. Okay. Now Alice and Bob are playing a game consisting of n rounds. In each round, the following 2-step process happens. Alice chooses two different colors. And what Bob does is Bob chooses an uncolored vertex and colors it with one of the two colors chosen by Alice. Okay. So now Alice wins if there exists an edge containing two vertices of the same color. Otherwise, Bob will win. Now you are given a graph. Your task is to decide that which player you wish to play as and win the game. Okay, so in the question, what they have given you is they have given you a graph with some nodes. There are some edges. There are some edges. Okay, and they have told you that there are two people, Alice and Bob, and there are three colors, one, two, and three. Now, what Alice will do is Alice will choose any two of these three colors. That is, let's suppose he can choose either 1, 2, 2, 1, or 3, 1. Let's suppose I'm choosing that he has chose 1, 2. Now, if he chooses 1, 2, what Bob will do is he will pick up any of these colors, either 1 or 2, and color the uncolored vertex of this graph. Let's suppose this vertex was already colored. This vertex was already colored. Let me mark it as well, that with which color it was colored. Let's suppose it was colored with 1, it was colored with 2. And if now Bob decides to color, if Bob has, Alice gave him two numbers, 1 and 2, and Bob has to choose any of these two numbers and color an uncolored vertex with that number. So let's suppose Bob chooses 1. If he do so, he will either color this vertex, or this vertex with 1. So he has options like he can color any of these. Let's suppose he colored this. Now again, Alice chooses these two numbers only. Now, if Bob tries to color any of these uncolored vertex with either 1 or 2, he will get that if he colors, let's suppose this with 1, he will get that, okay, there is an edge that is connecting two nodes having the same color. And if that is the case, Alice will win. If that is the case, Alice will win. So what Bob will decide over here? Bob will decide that, okay, let me choose 2 and I will color this particular node with 2. In that case, I will not have an edge that is connected by the same color. And then I will see what's the colors Alice are choosing in the next game. Okay. So what you want is, what the question wants you to do is that question tells you that you just choose any of these two people, either Alice or Bob, play the game from their end, and just try to win the game. So in case you are choosing Alice, so what you will do, you will choose any of these colors 1, 2, and 3, and you don't have the answer that, and you don't have the control in which uncolored node is getting filled. You don't have answer for that. That is something that Bob is doing. That is something the compiler is doing for you. And if you are choosing Bob, you are playing as a Bob. From any of these three numbers, he will give you two numbers. And now from these two numbers, you need to decide an uncolored vertex and color that particular vertex with any of these two colors. And you have to win the game. By winning the game, it means that uh, you have to have this condition that two nodes connected by an edge have the same do not have the same color. If you are able to achieve something like that, then the things are done. So how to solve this question? There are games of colors, right? So when we listen to colors, the most important thing that come to our mind is bipartite graph, isn't it? What are bipartite graphs? Bipartite graphs are the graphs in which all nodes can be colored with two colors with no adjacent node having the same color. So these are bipartite graphs. So now, which graphs are not bipartite? Graphs containing odd length cycles are not bipartite. Like for example, if I have graph something like this, and now if I just try to fill this graph with two colors, so let's suppose I fill it with one, and I want that adjacent node should not have the same color. So I will fill this with two, I will fill this with one, I will fill this with two. Now I don't have option for this particular node. I have to choose some third color three such that these adjacent nodes do not have the same color. So in case of odd length cycles, that is the length is 3. In case of odd length cycles, I can't, the graphs are told that they are not bipartite. And if this is not the case, let's suppose we have the even length cycle. In that case, we can every time say that the graph is bipartite. If we try to just fill it, 1, 2, 1, 2, 1, 2, 1. See, every edge has two nodes that are colored with two different colors, and we have used only two colors to color this entire graph. So these are called as bipartite graph. Now, how to use this particular thing is question. Now, if the graph is not bipartite, if the graph is not bipartite, I can make a claim that Alice can always win the game. Alice can always win the game if he every time chooses the same two colors. Why I am saying this? Because if let's suppose we were given three colors, isn't it? And if we are playing as Alice, we have the control to decide any two colors from these three colors from which Bob will decide, isn't it? So every time if we let's suppose choose one and two, so now I know that the graph is not bipartite. So Bob can't choose one color from this every time and color the graph such that adjacent nodes do not have the same color. Graph Bob can't do something like that because the graph is only not bipartite. So if the graph is not bipartite, I can say that okay, I will say that I will play as Alice. Alice will win the game, and every time I will choose only these two colors. I will never choose this third color. Every time I will give Bob option to choose the color from only these two colors. So he will never be able to color the graph such that adjacent nodes do not have the same color, right? Because the graph is not bipartite. So if the graph is not bipartite, so the solution becomes very simple that Alice will win the game and every time we will choose only these two colors. Okay. Now if the graph is not bipartite, so I make a claim that every time Bob can win the game. And how? See, if I say you that these are the nodes, this is the graph that you have. So what I tell you is just forget what numbers is giving. Just try to color this graph by using colors 1 and 2. So I color this with 1, this with 2, this with 1, this with 2, this with 1, this with 2, this with 2, this with 1, and this with 2. Such that the adjacent nodes do not have the same color. Okay. Now what Alice will do? Alice will choose two numbers between 1, 2, and 3 every time. Okay. So what are the three possibilities that Alice can choose? Alice will either choose 1 and 2, 2 and 3, or 1 and 3. I have simply wrote them in the shorted order. Okay. So these are the numbers Alice can choose. So if Alice chooses 1, 2, and 3, if Alice decide to choose 1, comma 2, that is 1 and 2. So now Bob has to select any of these numbers between 1 and 2 and color the uncolored vertex. So what I say is that every node, if let's suppose Alice decided to choose 1 and 2. So if you have 1 as one of the colors in 1, comma 2, and the nodes that I colored 1 by myself are not colored yet. This is something that I assumed the color. They are not colored yet. Okay, I will start coloring once I get the answers from Alice. So if I have the node 1 that is not colored yet, simply color them out. Again, if I get 1, 2 or 1, 3, I will just choose one and I will color the nodes that I decided to color as 1. Now, if I let's suppose now I get, once I color all the nodes that I decided to be 1, I colored them with 1. Now again, I get query from Alice as 1 and comma 2. If I get query from Alice something like this, in that case, since I know that all the nodes that were 1 are already colored, now I will start coloring the nodes that I decided to be 2. So I will just color this 2. I will color this 2. Okay, I will color this 2. Let's suppose I got this 1, 2, 3 times. So I colored these 3 2s. But if I get 1 and 3 now, so I know that all the numbers that I decided to be 1 are already colored. So how will I color 3 now? So it's not an issue now. Why? Because if I am getting 3 now, I can color the nodes that I decided to be 2 with color 3. Because I know that since all the nodes that were colored 1 are already finished, so I will have the adjacent colors of this color 2 as color 1 only. It's not possible that I will have nodes that are color 2 to the adjacent of this node that is already color 2, isn't it? So the one that I have decided to be color 2 but is not yet colored, now I can color them with 3. Now again, if I let's suppose get 2 comma 3, I can color it with 2 as well, I can color it with 3 as well. But while writing the code, I will prefer it to color with it too. And once I am done with this, I am done with coloring every node. So the job is done. So this is how I will implement this in my question. So what I claim that if the graph is bipartite, then it's very simple for me for Alice to win the game by just choosing 2 numbers every time, because I know that Bob will not be able. Sorry, if the graph is not bipartite, yeah, if the graph is not bipartite, then Alice can always win the game, because every time I will just choose 2 different colors, 2 same colors, and Bob will have option to fill the graph with only these 2 colors. So I know that he can't fill with only these 2 colors because the graph is not bipartite. But if the graph is bipartite, I say that okay, Bob can every time win the game. And how will I color the graph? So I know that since the graph is bipartite, I will just go and just pre-assume the colors with colors 1 and 2. And once I get the queries, I will fill them by the way I explained that if I am getting 1, 2, just just choose color 1 and fill the one that I pre-assume to be 1. And if those nodes are already filled, then just take 2 and fill them with 2. If I'm getting 2, 3, case, just fill the every node that I pre-assume to be 2 with 2. And if they are already colored, all of them are already colored. So just choose the nodes that I pre-assume to be color 1 and fill them with 3. It's not an issue, because I know that if all the nodes that I pre-assume to be color 2 are already filled, so like let's suppose this I pre-assume to be 2 and this I pre-assume to be 2, they are already filled. And these I pre-assumed to be 1, but they are not filled yet. So even if I fill it with 3, it will not be an issue. Isn't it? So this is so you are taking the number of vertices and m edges. Then you are constructing an adjacency vector of size n and taking m edges as input. That is basically you are now first of all constructing the graph. So you have you took u and v as the nodes. Since I'm storing them in zero-based indexing, I simply did u minus minus and v minus minus, adjacency of u dot pushed back v and adjacency of v dot pushed back v. Then for I will just store that what all nodes I have decided to be color 0 for color 1, what all nodes I decided to be color 1 pre-assume, and what all nodes I decided to be color 2. So I am just storing them in a vector of 2 size. Okay. So basically color of 0 will be a vector that will contain the nodes that I decided to be 0, that I decided to be color 1, and color of 1 will be a vector that will store the nodes that I decided to be color 2. Okay. So constructed this vector. And Since I will be doing a DFS call for that coloring purposes, I have maintained one visited vector and this node color n comma minus 1. These two vectors will become clear once I explain the code of DFS. So first of all, I will try to, what I will do is, I am not checking whether the graph is bipartite or not directly. For the ease of purpose, what I am doing is, I will just go to each and every node. I will just make a DFS call and try to color the adjacent nodes with the different color. That is, if I have my graph something like this. So I will simply start a DFS call from here, color this node as 0, then color this node as 1, then color this node as 0. Now from here in the DFS, I have two options, either to go here or go here. So what I will do, I will try to explore here. I will go here once, then I will go here, then I will go here. And when I try to go here, what I will see that, okay, this node is already visited. And if the node is already visited, I will just simply check that if the visited node does not have the same color as the color that I have. If that is the case, I know that the graph is not bipartite. And if that is not the case, I can say that the graph is bipartite, isn't it? So that's what I have done. So initially I have started my DFS call from 0. So marking the node color of this node 0 as 0 and marking visited of 0 as 2. And I know that since I have colored it with 0, so what in my example, I took the colors 1 and 2. Over here, I am taking them as 0 and 1. Okay, don't get confused by that. So just marking color of 0, pushback 0, that okay, to this color of 0, I have node 0. And I make a simple DFS call with the node 0, and initially it has color 0 because it will just oscillate between two colors 0 and 1, isn't it? So let's see this DFS function. So I have made this lambda function. You can also make it outside of this main function. Okay, it completely depends on you. So making this DFS function, it's a void function. So what this function will do, I have one value f equals to 0. So if any time it finds that, okay, I have these two, both of these two nodes visited, I am standing over here. In my adjacency list, I have this node, but this node is already visited and it has the same color as the color I have. In that case, I will simply mark f as 1. And for every for this function, I have node and the color of this particular node. So I am going to the adjacency nodes of this particular node. And if the adjacent node is already visited, so I need to check what is the node color of that adjacent node. If the node color of that adjacent node is similar to what the node color I have, in that case, I will simply mark the value of f as 1 and return. Else, I will mark that particular adjacent node as visited, color it with a different color that I have. I have C, so I will color it with not C. That is, if C is 0, I will color it with 1. If it is 1, I will color it with 0. So I will simply mark the node color of IT as not C, and in colors vector of not C, I will push back this particular node and make a DFS call, a simple recursive call to this particular node IT with the color not C. Because for this particular node, the color is not C. Once I am done with this, and if after doing the DFS call, I have the value of f as 1, this means that the graph is not bipartite. In that case, I can simply output Alice, and I can just every time for every particular node, I can uh, give the input of colors to the Bob as 1 and 2, and simply take what what color he is filling it with, and what node he is filling it with, and what color. Simply take the input. But I know that the answer will always be Alice because I will have two adjacent nodes having the same color if the graph is not bipartite, and every time I am giving options from only these two colors. Now, if this is not the case, that is the value of f is not equals to 1, that means the graph is bipartite and Bob can win the game. So I simply printed Bob, made my value of I as 0 and j as 0. So what does this will tell me is that I have these two vectors, right? This is color of 0. This is color of 1. So these are colors. These are the ones that I decided that, okay, I pre-assume them to be to fill them with color 1. So this contains the node values that I pre-assume to be color 1, and this contains the node values that I pre-assume to be color 2. So I am just starting from their start, so marking I as 0 and j as 0. I will one at a time, I will pick nodes from them. So initialized my I to 0 and j to 0, and now for every particular node, I take the inputs of the colors that Alice is providing to me, the options that Alice is providing to me, and I simply, if the value of u is greater than v, I am simply swapping u and v so that the u contains the minimum of u comma v. Now, if the value of u is 1, so I will simply check if I have the nodes left that I pre-assumed to be color 1. So I have that. If I have that, so in that is I is less than color of 0 dot size. In that case, I am simply filling that particular node with color u. And you know that since I have stored all the things in zero-based indexing format, but the answer wants me the answer in one-based indexing format. So I am simply printing this node plus 1 for converting this node to one-based indexing format, comma, the color u, and simply incrementing the value of I because this node now is already colored and I will not color it again. Else, if all the nodes that I pre-assume to be 1 are already filled, so I know that I need to fill the other one. I need to fill with color V now. I can't use color U, that is color 1. And I will fill the ones that I pre-assumed to be color 2. The ones I have pre-assumed to be color 2 now can be filled by either color 2 or color 3 as well. So if the value of U is 1, the value of V will either be 2 or 3, isn't it? So I go to the node that is in color that I pre-assume to be color 2, simply fill it, convert it into one-based indexing format, and fill it with color V and simply increment my pointer. Else, if the value of U is not 1, so what are the colors I am given? I am given colors 2 and 3 because the U I know was the minimum value, isn't it? So now I have the colors 2 and 3. So first of all, I will try to fill the nodes that I pre-assumed to be color 2. So if I have those nodes left, so if j is less than color of 1 dot size, simply fill them, converting to one-based indexing format, color it with U, and simply shift the pointer j. Else, if I know that all the nodes that I pre-assume to be color 2 are already filled, so now I am going to fill the nodes that I pre-assume to be color 1, so I can fill them with color 3 as well now, isn't it? So just printed the node value, color V, and simply incremented the pointer. Once I am done with this, my job is done. Like I have done this for each and every node, and my job will be done. So this was the solution for this problem. I hope all the solutions were pretty clear to you all. Oh,